So, hello everyone. My name is Shubham, and I'm a PhD research scholar in Department of Applied Mechanics at Delhi. So, this is related to this live section is related to clearing your doubts if you have any, or discussing the questions related to the content taught in week one of the course Solid Mechanics. So, I'll be starting with solving few questions related to what has been taught in week one. So, let me start. So, the course name is Solid Mechanics, and this is a live session related to week one. So, in week one, you would have studied mathematical concepts, that is working with vectors and tensors. Also, you would have studied related to traction vector. Traction vector. And the third lecture was based on stress tensor and its matrix representation. So, let me start with few questions. So these questions will aid in developing your concepts further. Theory has been covered a lot in lectures, so I'll try to focus more on questions. So the first question is, let's say you have a second order tensor, which is denoted by Sij, and Sij in matrix form Sij has these components 102, 012, and 303. And also you have a vector or first order tensor, which is denoted as Ai. So let me put this in bracket. So this is 1, 2, 3. So you have a second order tensor and a first order tensor. So the first part is you have to evaluate
Yes, sir. Yes, sir.
so you have to evaluate Sij and Sij. So S is so this is a matrix multiplication of S with S only. So here I and J, you're able to see that I and J are repeating indices because here I is repeating 2 times and J is also repeating 2 times. So there will be summation over I and J because repeated indices imply summation. So let's do that, and I will go from 1 to 3 because I mean it has 3 rows and 3 columns, so that's why I will go from 1 to 3. J will also go from 1 to 3. So this actually means is I is going from 1 to 3 and sigma J is going from 1 to 3. Sij times Sij. So in explicit form, I have written Sij is equal to sigma I going from 1 to 3, sigma J going from 1 to 3. and SI. So now if you will put all the values, so what will be that? So let's firstly let's put I is equal to 1. Let's start with I is equal to 1 and j going from 1 to 3. So you will get S1 1 S1 1 plus I is still 1, so and j is 2, so S1 2 S1 2 plus I is still 1 and j is 3, so S1 3 S1 3 plus. So let's say now I becomes 2 and then j again will go from 1 to 3, so S21 S21 plus S22 S22 plus S23 S23. And now your I will be 3 and j will again go from 1 to 3. So I will be 3, so it will be S31 times S31 plus S32 S32 plus S33 S33. Okay, so this will be a scalar because all the values are getting added up. So this essentially is a scalar. So if you will do all the calculations, so S11 times 11 will be 1, S12 times 12 will be 0, S1313 will be 4, plus S2121 will be 0, S2222 will be 1, this is 4, 9, 0. Simply have to square all the elements of S and add them. So if you add, you will get 28. So 28 is the answer. So this was a very straightforward problem. So in lectures, in a double contraction, just let me see, the screen has got unshared. Yeah. So in lectures, you would have studied double contraction. So this is essentially double contraction of S with S only. So this you can also write as S is a second order tensor. It is double contracted with S itself. So this is double contraction. Double contraction of two second order tensors leads to a scalar value. So that's why we are getting a scalar here. So this was the first part. Now the second part will be second part is you have to do AM times AM. So M is again a repeating indices. So can you try doing this? So A is given to you. So A is this one. A is AI is 1, 2, 3 is a vector. So you have to calculate AM times AM. It's very easy. Can somebody tell me the answer? Okay, so let me do it. So since again M is a repeating indices, it is coming two times. So that's why there will be summation over M, and M will go from 1 to 3 because A has three components. So now, so this will be essentially M going from sigma M going from 1 to 3 AM times AM. So this is nothing but A1 square, A1 times A1 plus A2 times A2 plus A3 times A3. So it's a dot product of A vector with A vector, right? So if you do, you will get 9 plus 4 plus 1. That will be 14. Okay. You can ask me if you have any questions. These were pretty straightforward. problems. Okay, so the third part is C part. So C part says, so you have to calculate SMN AM times AN. Okay, so again here you are able to see that this M is coming two times and this N is also coming two times. So that's why there will be summation over both M and N, because M is also a repeating indices and N is also a repeating indices. So we'll go from I going from 1 to 3. Sorry, there's no I actually, there's M and N. So it will be M going from 1 to 3. So N sigma N going from 1 to 3. So, and then you have S M N AM times AM. So can you tell me whether this will be a vector or a scalar or a second order tensor? So this result, what that result will be? So will it be a second order tensor, because it's a multiplication of a second order tensor with a vector, and then again we are multiplying with the vector. So what will be the answer? So will it be a second order tensor or a first order tensor or vector or a scalar? So to answer this question, what you can do is you can just look at the indices. So there are no free indices here. Free indices means independent indices which are not repeating. So here M is also repeating, N is also repeating. So there are no free indices, so that's why it will be a scalar. Whenever there will be no free indices, when each of the indices will be repeating in nature, so that will be a scalar value. If there is one free indices, that will be a vector. If there will be two free indices, then that will be a second order tensor. Similarly, three free indices imply third order tensor. So here there is no free indices, M is also repeating, N is also repeating, so that will be a scalar value. So you can just now put, so I'll start with M is equal to 1, N going from 1 to 3. So M is 1, so M is 1, N going from 1 to 3. So now N will be 1 first. So first value is this. Now M is 1, N is 2. So that will be A1, A2 plus M is 1. So this will be 1, N is 3. So that will be A1, A3 plus. Now your M will be 2 and N will again go from 1 to 3. So S2, N1, M2, N1 plus. Again N will be 2 plus. M will be 2, N will be 3. So S2, 3, A2, A3 plus. Now your M will be 3, N will again go from 1 to 3. So M is 3, N is 1. M is 3, N is 1. Then M is 3, N is 2. Then M is 3, N is 3. Okay. So you're able to see that all the values are getting added up. So that will lead to a scalar value. So you can calculate all these values. So S11, A1, A1. So that will be 1, because S11 is 1, A1 is also 1. So that will be 1 plus S12, S12, A1, A2. So S12 is, so this is S12, S12 is 0. And A1 is 1, A2 is, so that will be 0 again. And similarly you can add 6 plus 0 plus 4 and so on. So if you will add all these values, you should get 59. So is there any question? You can ask me. So this was related to multiplication of second order tensor and a vector, and it was more of understanding what are initial notation, how to deal with initial notations, how to assess whether the initial, I mean multiplication with initial notations will lead to a scalar or a vector or a tensor. So now going to question 2. So question 2 says, let me just write the question first. So it says, suppose we have a second order tensor A. So A is a second order tensor, so I'm denoting second order tensor by putting two underbars below A, two underscores below A, and there is another second order tensor. So that is B. So and there is a relation between these two second order tensors such that, I mean, A is A transpose and B is minus B transpose. So A is a symmetric matrix and B is a skew symmetric matrix. So you have to show that the product of tensor A and B is 0. So by product I imply double contraction. So we have to show that double contraction of A and B is 0. Okay. So double contraction of A and B will be A double contracted with B. So that will be scalar value because double contraction reduces the order of a tensor by amount 2. So since it is a second order tensor, it will become a scalar. So this will be Aij times Bij. So since I is also repeating 2 times, J is also repeating 2 times, so this is a scalar. There are no free indices, there are only repeating indices. So now we have to show that Aij times Bij will be 0. So how we can show is, let's say you have Aij times Bij. So Aij times Bij can be written as so from here actually let me use these relations. So A is A transpose, so Aij is equal to Aji. Okay, so this is given to you here because A is A transpose, so Aij will be equal to Aji, and B is minus B transpose, so Bij is equal to minus Bji, right? Now if you substitute here in this first Aij times Bij, so Aij times Bij, that can be written as Aij can be written as Aji and Bij can be written as minus, I'm putting here minus of Bji, right? This we can write. Now this J is a repeating indices and I is also repeating indices. So we can interchange repeating indices because these are going to lead to a scalar value only. It doesn't matter if you interchange I with J, it will not affect anything. So let me just interchange. So I'll show you how it will not affect anything. Interchanging indices I with J here. So if we'll do that, so I'm not interchanging on the left hand side but only on the right hand side. So if you'll do that, so you will get Aij times Bij, so that will be equal to minus of Aij times, because I've replaced I with J and J with I, so it lead to Aij times Bij. Okay. Now you bring this Aij times Bij, minus of Aij times Bij to the left hand side. So Aij Bij plus Aij Bij will be 0. This implies 2 times Aij Bij will be 0. So this implies Aij times Bij will be 0. So we have proved that if a matrix is, if A is a symmetric matrix and B is a skew symmetric matrix, then double contraction of both of these two matrices is going to be 0. Now let me prove that if we interchange the indices, it is not going to, if we interchange the repeating indices, it's not going to affect anything. So let me just take this A ji times bji. So if I mean summation will be written as, it will have a long summation. So let me just assume that for the timing, just to show you that interchanging the repeated indices won't affect anything. Let me just assume that j is going from 1 to 2 and I is also going from 1 to 2. So let me just put it here, I is going from 1 to 2. Although I and j are both going from 1 to 3, but just to prove. So this will be, so firstly you have to put, let's put I is equal to 1, and so j will go from 1 to 2. So this will be a11 b11. So now I is 1, j is 2. So a21 b21 and plus, now I is 2 and j is 1. So 1 2 b12 and then I is 2, j is 2, a22 b2. So you have summation of all these four quantities. Now you just interchange I and j. So these are repeating indices. So if you interchange them, it is not going to affect anything. So let's interchange them. So at the place of j, I will place I, and at the place of I will put j. So this will be aij bij, again going from 1 to 2. So that will be, let's say I will be 1 first and j will be 1. So a11 b11 plus I will be 1 and j will be 2. So a12 b12 plus I will be 2, j will be 1, a21 b21 plus a22 b2. So you see here that these two summations are essentially equal, because here a11 b11 a11 b11 is present, a21 b21 a21 b21 is present, and a12 b12 a12 b12 is also present, and a22 b22 a22 b22 is also present. So interchanging the repeated indices will not affect your result. Okay. So this was, I hope you would have understood. If you have any questions, you can ask me. Okay, so let me go to the next part. So this is question 3. So it says you have to evaluate uh, del ij, del ik, and del jk, where this del is known as Kronecker delta function. Kronecker delta function. So this is a function which you would have studied or not studied, but let me tell you. So this is a function whose value is 1 if I and j are equal. So del ij will be 1 if I will be equal to j, and this will be 0 if I is not equal to j. So So let me just ask, uh, if I say that what will be the value of del 1 2. So since I is not equal to z, so this will be 0. Similarly, the value of del 3 2, so that will also be 0. And value of del 1 1. So because I is equal to j, so this value will be 1. Okay. Now let's solve our question. So we have to solve del ij comma del ik. I mean del ij times del ik times del jk. So we have to solve that. So let me just do that. Del ij del ik times del jk. So firstly I am just multiplying first two chronicle delta functions. So now from here you are able to see that, let's focus on this function. So this function will be 1 only when I will be equal to k, otherwise it will be 0, right? And if this is 0, all the terms are going to be 0. One more thing before that, all the indices present in this question are repeating indices, because I is also repeating 2 times, j is also repeating 2 times, k is also repeating 2 times. So this is going to be, the value is going to be a scalar, because all the indices are repeating, free indices are not present. Okay, so there will be summation of, so based on the value of I, j and k, there will be a term, and subsequently there will be a summation of all the terms which will come from the product of these three chronicle delta functions. And if any of these chronicle delta functions become 0, that term will be 0. So that's why this term is going to exist only when I will be equal to k. Otherwise, this chronicle delta function will go to 0. So let's put I is equal to k here. So if you put I is equal to k, so I'm going to put this in the chronicle delta function just at the left hand side of this chronicle delta function. So I will be equal to k. So del ij times del ik can be written as del ik, because, sorry, del kj, because I have put this I equal to k. So I have substituted this I with k. Okay. And this chronicle delta function, these two chronicle delta function has been merged now. Okay, so when I will be equal to k, this will be equal to 1. So here also we'll have to substitute I is equal to k. So now we have del kj times this chronicle delta function which is present outside, del jk. Now again look at this chronicle delta function which is present on the right hand side. So this will be 1 only when j will be equal to k, otherwise it will be 0. So since it will be 1 only when j is equal to k, so let's put here j is equal to k, so it will be del kk. So del k was there and I have put j is equal to k, this should be del kk. Now k is repeating 2 times, so k is going to be, and k will go from 1 to 3. So let's put, so this will be, this is the repeating indices, so it implies summation. So it will go from 1 to 3. So del 1 1 plus del 2 2 plus del 3 3. So this will be 1 plus 1 plus 1, so that will be 3. Okay, so let me go to the next question. Before going to the next question, I would like to tell about the tensor product or dyadic product. So the product between two, I mean the tensor product or dyadic product, it will be denoted by this circle and a cross in it. So you will have, this is, this we will use to denote dyadic product. This is again a type of product between two tensors, and only cross represents the cross product. So you would have learned about cross product in the lectures. So it is a product between two vectors. So now let's say you have two tensors, two second order tensors. So A dyadic product B, so that is one second order tensor, times C dyadic product D. So A is a vector, B is a vector. So when I'm doing tensor product or dyadic product between two vectors, it will lead to a second order tensor. Similarly, C is also vector, D is also vector. And I'm doing a tensor product or dyadic product between two vectors, so that will lead to a second order tensor. So, and this represents single contraction between two second order tensors. So I can just represent this A dyadic product B as tensor A, and this C dyadic product D as tensor B, and I can just say that this is the first, single contraction between two vectors. When there is no sign here, it means it's a single contraction between two tensors. So single contraction, so the definition of single contraction is whenever there will be single contraction between two second order tensors, so what you have to do is, so you have to multiply, you have to do dot product of the inner vectors. So these two vectors are present inside, so you have to do dot product of these two inner vectors, the vectors which are present inside, and you have to do dyadic product of the vectors which are present at the extremes. So you have to do dyadic product of A and D. So answer will be A dyadic product D and then B dot C. So this is dot product between two vectors. So this is known as single contraction. Okay, so now there will be a double contraction also. So definition. So this was the definition of single contraction. You can say that this is, so this is definition of single contraction. Now going to the double contraction. Let's say this definition of double contraction. So here you are able to see that single contraction between two second order tensors lead to a second order tensor itself, because this is a scalar. Dot product between two vectors will be a scalar, and this is a second order tensor. So single, if we take a second order tensor, another second order tensor, and do single contraction, so the answer will be a second order tensor only. Now let's see, if we do double contraction, you might be knowing that this will lead to a scalar value. So let's do double contraction between these two second order tensors. So A dyadic B second contraction, double contraction times C dyadic product D. So what you have to do now, you have to pick A and C and B and D. So you have to pick these, alternate vectors, and you have to do dot product between them. So this will be A dot C times B dot D. So this will be a scalar because this is also a scalar, this is also a scalar, and these two are multiplied together. So this will be a scalar. Now based on these two definitions, we have question 4. So question 4 says that you have to prove that A, which is a second order tensor, times another second order tensor which is A dyadic B, so that is equal to A, and then second order tensor multiplied with vector, then dyadic B. So you know that this second order tensor multiplied with vector will be a vector. So this vector times this vector dyadic B should be proved equal to this tensor times this tensor. Okay. So you cannot actually here, just to let you know that you cannot write this quantity as A times A dyadic A times. You cannot distribute a second order tensor over the components of another other second order tensor. This is not this is not allowed. Okay. So let me do the solution. So you can try by yourself first. I'll give you 2 minutes, then I'll tell you how to do this question. Okay, so let me do this. So I'm just so I'll start with this quantity here. So tensor A can be written as Aij Ei diadic Ej, right? So this is the second order tensor, and then this is multiplied with A diadic B. There is no sign, it means it is the first contraction. I mean, it is a single contraction. So since this is a single contraction, what you can do is you can multiply inner vectors. You have to do dot product of these two inner vectors, and you have to do diagonal product of these two outer vectors, right? So now this can be written as Aij. So then A dotted with Ej, because you have to do the dot product of the vectors which are present inside, and then you have to do diagonal product Ei diagonal B, right? Okay, so now what will be this A diagonal A dot Ej? What will be that? Okay, so A can be written as Ai Ei. This is a vector, so A can be written as Ai Ei, and that is dotted with Ej. So you know that this Ej, Ei, Ej. So these are the basis vectors like E1, E2, E3. So when I will be equal to j, then their dot product will be 1. And if I is not equal to j, you know that it represents the three coordinate, three axes of the coordinate. Now these three axes are orthogonal to each other, perpendicular to each other. So the product of these two, the product between any of these two vectors will be 0, because these are at 90 degrees to each other. But a vector dotted with itself will give its magnitude, so a square of the magnitude. So you know that these vectors have a magnitude unity. So it will only be non-zero when I will be equal to j, otherwise it will be 0. So we can write it as ai del ij, where del ij is a chronicle delta function. So you know that this will only be 1 when I will be equal to j. So since I will be equal to j, so this is aj. Okay. So a dot ej will be aj, and it's very simple also, because you are finding the component of a vector along ej axis or along ej unit vector. So that will be the jth component of a vector. Okay. So let's put the value of a dot ej in equation number let's say this is 1. So equation number 1. So you will get aij times small aj and then ei dividing b. Okay, now you know that what is this? So this is going to be a vector. So let me just tell you. So this aij times aj. So here there is, so j is a repeating indices and I is a free indices. So since there is only one free indices, so this is going to be a first order tensor or vector. Okay, so this is going to be a vector. So let me call it as vector p. Okay, vector p. So if I substitute above, so um, also let me just tell you what is this. So this is essentially matrix A times vector A. Okay, because if you sum over J, so and if you want to find first component of this vector, so I will be 1 and j will go from 1 to 3. So this will be a11. So let me just so let me put that equal to p. So first component will be p1 will be, so this will be a11 small a1 plus a12 a2 plus a13 a3 a13 small a3. So similarly p2, so that is a21 a1 plus a22 a2 plus a23 a3. Similarly p3, so if I just denote, so this will be pi actually. So p3 will be a31 a1 plus a32 a2 plus a33 a3. So this is nothing but matrix A times vector A. Okay, so let me just put it. So this, let's say this is equation 2. So let me put in equation 2. So a times a, so I can just write as aij times aj. So that will be a times a times ei divided b. So um, so this is a vector actually. So let me put as pi. Okay, so aij aj is pi. So I have just put it here. So pi ei is vector p. So vector p diagonal b. So this leads to this answer. And vector p is again this vector a times a diagonal b. So we have proved. So we have proved that a times a diagonal b. So we started with, so that is equal to a and single contraction a diagonal. Let me tell you again how we have done this. So we have started with left hand side. So here we have to do a single contraction between this second order tensor capital A and this second order tensor small a dividing small b. So that should be put equal to second order tensor times vector dividing vector b. So for that I have written the second order tensor as aij, ei dividing ej, and then it is single contracted with a dividing b. So with the definition of single contraction we get aij, and this vector is dotted with this vector, so a dot ej, and then there will be there will be a direct product between the outer vectors, so ei direct b. Now a dot ej will be aj because this will denote the jth component of vector a, and aij times aj will be some vector, so that I have denoted with p. So this will be pi ei, so this will be again be, so this will be aij times aj and ei. So aij times aj will be some vector pi, and pi times ei is again some vector, so that will be p vector. So this will be p vector times b, and p vectors is nothing but the multiplication of this matrix A times vector b, vector A. So that's what we have put here. So this is p times b, and p is multiplication of this second order tensor and this vector and dividing b. So that's why we have put this quantity equal to this quantity. Okay, so you can ask me if you have any questions. Now on to the next question. So next question says you have to prove that vector A dividing vector B. So this will be second order tensor, single contracted with second order tensor A. So that should be equal to vector A diadic E transpose B. Okay. It means when you bring this second order tensor to this with this vector, so it will come to the left hand side with a transpose. So you can bring it here, but this will get transposed. So I'm giving you 2 minutes to solve this. This is question 5 actually. Okay, so let me start. So I'm just taking this left hand side here. So A times A direct B times, so capital, tensor A can be written as Aij Ei direct Ej. Okay, so Aij is a scalar now, so you can bring it to the left hand side. So I'm just bringing it here. Aij, now it will be A times A direct B times Ei direct Ej. Okay. So again, there is a single contraction between two second order tensors. So these two quantities will get, these two vectors will be dotted with each other, and these outer vectors, there will be diagonal product between these two outer vectors. So this Aij, so diagonal product will be B dot Ei, and there will be a, sorry, this will be dot product. So dot product is B dot Ei, and diagonal product will be A direct Ej. Okay. So Aij, so B dot Ei is again Bi, right? B dot Ei means you will get ith component of B, when you will dot B with the unit vector Ei. So you get ith component of B, and A can be written as AK EK, right? Because A is a vector, so we can write it as AK EK. So this is what we have got. Okay, so now we have to prove A dyadic. So let me keep, so since we have to prove A dyadic A transpose B, so I'm putting A to the left hand side, because we have to get A at the left hand side. let's just put A at the left hand side. So you will get AK EK direct, this is also vector, EJ, and then AIJ times BI. And then because this is AIJ times BI is some scalar quantity, there is no vector associated with this, so I can just shift this here also. I mean in between these two. So because EK and EJ are vectors here, AK, AIJ, BIJ all are magnitudes. So this AK times EK direct. So I can just bring AIJ times BI and EJ. Okay. So let me tell you what is this AIJ times BI. So this AIJ times BI is nothing but some vector which can be denoted as so this is nothing but PJ, because here you are able to see J is the free indices and I is the repeating indices. Okay. So let me just find, so this will be a vector and this will be denoted by PJ because I is the repeating indices, J is the free indices. So now PJ, so let's find P1. So P1 will be I is repeating, so there will be summation over I, so J will be 1. So A11 B1 plus, since J is 1, so it will be A21 B2 plus A31 B3. And similarly you can find P2 and P3. So now you will observe that vector P will be equal to, so all components of P, P1, P2, P3, so that will be equal to A transpose, because now here you don't have A11 B1 A12 B2, now you have A21 B2, so this is something A transpose, so this is A transpose times B. Okay, so you can put in equation, let's say 3, so you put in equation 3, you will get AK times EK, right? AIJ BI is PJ times EJ. PJ times EJ is nothing but vector P. So AK times EK direct. PJ is vector P. So AK times EK is vector A and PJ times EJ is vector P. So this is A direct P, vector P, and vector P is nothing but A transpose B. So that's why we have proved it. So that's what we had to prove actually. Okay. So is there any question? You can ask me if you have any questions. Okay, so let me go to the next question. So before moving to the next question, I would like to introduce the permutation symbol. So let me just write alternator or permutation symbol. Okay, so permutation symbol is denoted by epsilon ijk, and I'm just going to define it. So it's the definition of this permutation symbol. The definition is it will be 0 if any of the two indices are same. Okay. And this is going to be 1 if all the three indices are different and in cyclic order. If all the three indices are different and in cyclic order. Okay. And there is one more thing. It will be equal to -1 if all the indices are different and they are not in cyclic order. So this will be -1 if all the three indices are different but not in cyclic order. So let me tell you what is cyclic order. So I will go from one, I and J and K will all three will go from 1 to 3. So let me just write 1, 2, 3. So cyclic order means 1 will come after 2, 2 will come after 3, 3 will come after 1. So, and this is if order, this order is maintained. So either it is 1, 2, 3 or 2, 3, 1, okay, or 3, 1, 2. This order is maintained. This is cyclic order. If this order is maintained, then the permutation symbol will have value 1, otherwise it will have value -1. So let's see. So what will be the value of epsilon 1, 1, 1? Because let's see in which category it is falling. So it is falling into the first category because the two indices are, two indices, all three are same actually. So that's why its value will be 0. So none of the indices should be same, otherwise its value will be 0. So epsilon 2, 2, 3, let's say that this one. So this will also be 0 because these two indices are same. Now let's see what will the value of epsilon 2, 1, 3. So let's see whether it is in cyclic order or not. So cyclic order, since it is starting from 2, so it should be 2, 3, 1. But this is 2, 1, 3, so it's not in cyclic order, so its value will be -1. And now let's see what is the value of epsilon 3, 1, 2. So you are starting from 3, so 3, 1, 2. So now it's in cyclic order, and that's why its value will be 1. Okay. So this is the definition of permutation symbol. And let's say you have this product. So this is a very, I'm just writing a note here. So there is a special kind of product between permutation symbol. So let's say you have this epsilon ijk. Let me just use different color. Let's say you have epsilon ijk times epsilon pqk. So here you are able to see that k is a repeating indices, right? And I and j are free indices, p and q are also free indices. Okay. So there are 4 free indices in this and 1 repeating indices. So this product will be equal to, how you have to write, you just remember this. So this will be equal to, you have to write Kronecker delta 2 times here and Kronecker delta 2 times here. And you just see the first case, you see the first 2 free indices. The first 2 free indices is I and j. Okay. So you put I here at the first place, first Kronecker delta, the first place of second Kronecker delta, you put j. Okay. And again you put I and j here also. And put minus sign here. And then you see the next 2 free indices. So next 2 free indices is this one. So you put the next 2 free indices here, p and q. And now while writing these next 2 free indices in second Kronecker delta products, you just interchange them. You write q and p. So how we have written? Firstly, we have taken first 2 free indices. So this is ij, and then we have taken the second free indices, second set of free indices. So there will be PQ, so it will PQ and QP, and there will be a minus sign. Okay, so this you can remember. This is a product between, I mean, some special kind of product between two chronicle delta functions. So let's see. Based on this, I can give you question 6. So what will be the value of epsilon ijk times epsilon ijk? So since all the three indices are repeating, I is also repeating 2 times, j is also repeating 2 times, k is also repeating 2 times. So there are no free indices here. All the repeating indices are there. So that's why it will be a scalar value. Let's write it. So there will del here minus 2 chronicle delta here. So we take first free indices. So first free indices is ij. So I just write ij time and ij. And second free indices is also ij. So I write I here, j here, and j here, and I here. So del I, so this will be del I times del jj minus. So this will, so there is the product of two Kronecker delta functions. So this will only be equal when j will be equal to I. So since j will be equal to I, this will be 1 and this will be del II. So this is del II. Okay, so now here we have two, I mean we have a repeating indices, here also we have repeating indices, here also we have repeating indices. So if you do summation, so this will be del 11 plus del 22 plus del 33 first quantity, and then again jj, so there is a jj and j is a repeating indices, so there will be summation over j going from 1 to 3. So this will be del 11 plus, and again del ii is there, so minus del 11 plus del 22 plus del 3. Okay, so this will be 3 times 3 minus 3, so that will be 6. So this is the answer. So I hope you would have understood something. Now let me go to the next question.
Yes, sir.
So let me go to the next question. So question 7 says you have to prove that vector A cross product vector B cross product C. So it is known as vector triplet product. So this should be equal to A times C, I mean A dot C times B minus sign is here, A dot B times C. You have to prove this. So you have to prove that, so B cross C will be a vector, because cross product of two vectors will be a vector. Again it is cross product with another vector, so this is going to be a vector. That should be equal to A dot C times a vector minus A dot B times a vector. So this is also a vector, because this is scalar times vector minus scalar times vector, so that will be a vector. So you have to prove this. You have to prove this using permutation symbol, because you can write cross product in terms of permutation symbol. So let me just, you can just first try. So can you just tell me that how to write B cross C with the help of permutation symbol? Yeah. Have you seen somewhere how to write a cross product with the help of permutation symbol? So let me tell you how to write it. So cross product between two vectors with the help of permutation symbol. So it can be written as, let's say it is epsilon ijk. Okay. So it will be Bj, Ck and Ei. Uh, how I have written this, so let me just prove you. I mean prove something. So it's very easy. Um, so to write vector, I mean this cross product, you write I, J, K here, or let's say E1, E2, E3, E1, E2, E3, right? Even cap, let's say. E1 is the first component of the, I mean, this is unit vector along x-axis and unit vector along y-axis and unit vector along z-axis. So E1, E2, E3. Now you write components of B. So this is B1, B2, B3, and now you write component of C, C1, C2, C3, and you take a determinant of this. So this is going to be E1 times B2 C3 minus C2 B3 minus B2 times B1 C3 minus C1 B3 plus E3 times B1 C2 minus C1 B2. Okay. So if you compare the first quantity E1 times B2 C3, so now let's see this definition. So I told you that when I, J, K are in cyclic order, so let me write 1, 2, 3. So 1, 2, 3, and cyclic order will be this one. So when I, J, K will be in cyclic order, you will have the value of this will be 1, and if this is not in cyclic order, value of this will be minus 1. So this term is 1 actually. This term is positive, so let's evaluate this term only. So it is E1 means I is 1, and B2 means J is 2, and K is 3. So since it is epsilon 1, 2, 3, so epsilon 1, 2, 3 will be 1. So it will lead to first term of this vector. Now let's put, so I is 1 only, but J is 2, sorry, J is 3 and K is 2. So it is 1, 3, 2. So 1, 3, 2, you see it is anti-clockwise, that's why the value is minus 1. What I'm saying is the first term of this quantity is B2C3 epsilon 1, which can be compared with epsilon ijk bjckei. Okay, so if you compare now, so your I will be 1, B and J will be 2, K will be 3. So that's why epsilon 1, 2, 3 will be 1. So this is 1 times B2 C3 E1, right? This is what you are getting. Now the second term here is minus E1 C2 B3. So let me just write. So this is nothing but you can write it as epsilon 1 3 2 B3 C2, right? And E2 E1, so right. So here your I is 1, J is 3, and K is 2. So 1 3 2 is there. So 1 3 2 we are going anti-clockwise. So that's why its value will be minus 1. So that's why this is. So similarly, you can express all the other terms through this expression. So that's why the cross product between two vectors can be written with the help of permutation symbol. Okay. So let me get back to where I had started. So B cross C can be written as epsilon ijk bj ck and ei. Okay. So now initially we had to prove this. So let me put in this expression. So if I put in this expression, so I had this expression A cross B cross C. So B cross C I have already written. So A can be written as AM EM. I'm using some other indices for A. Cross product. Okay, so cross product times you just add B cross C, which is epsilon I J K B J ck ei. Okay, now you combine all the magnitude terms, so this will be am, let me first write epsilon ijk, so this will be epsilon ijk am bj ck and em cross ei. Okay, this is fine. Okay, so let me, this will be epsilon ijk am bj ck. Let me also write this in terms of commutation symbol, so that will be epsilon, let's say I'm introducing n mi and mi, yeah, nmi. So magnitude of em actually, so magnitude of em, so, and magnitude of ei times en. Obviously en will be perpendicular to em and ei. Em will be perpendicular to the plane containing em and ei. Okay, so this will be 1 actually, because this is, so I have just applied the definition of permutation symbol. So since b cross c was epsilon ijk bj ck ei, similarly em cross ei will be epsilon nmi. So second, last two indices should match with these vectors. So that's why it's nmi, em, ei, en. Um, so these two will be 1. So now we will be left with am, bj, ck, and epsilon ijk times epsilon nmi times en. Okay. Now since this is a product between two canonical delta functions, so let me write this. So I mean this is a product between two permutation symbols, not canonical delta. So this can be expressed in terms of canonical delta. So that is, you write del here, minus del here. So firstly, you go with first repeating indices as first two free indices. So these are I and j. So here you get ij, and here also you get ij. Then you go to, oh, just wait a minute. There is one more setting that needs to be done. So here actually I is a repeating indices. Okay. So this repeating indices in this product should come at end. So I'm just putting this I here. So we have I, j and k like this. I, j and k going in cyclic order. So if I want to put I at end, so I can write j, k, I. Okay. So let me just write, because it will not change anything. I can just put it in cyclic order. So ck, so epsilon j, k, I can be written, and this is epsilon n, m, I. This I have done because I want to put the repeating indices at the end. Here I want at the end. So because in this definition, this repeating indices is at the end, so that's why I've done it. So this should be equal to am bj ck canonical delta, and then canonical delta minus canonical delta times canonical delta and em. So first two free indices are j and k, so it will be jk and jk, and last two free indices are n and m, so nm and m. So nm will be as it is, and then here it will be interchange. Okay, so I forgot what we have to prove. Okay, we have to prove this. Let me just combine these terms. So we have am bj ck del jn del km en minus am bj ck del jm del kn and en. Okay, so here now let's see. So when this j will be equal to n, then only this value will be 1. So we can put this j equal to n here. So j will be replaced with n. And when this k will be equal to m, only then this will be 1. So k can be replaced with m. So here I am replacing this k with m. Okay. So if you do that, so am j will be replaced with n. So this is bn, and k will be replaced with m. So this is cm, and then en minus. So here if you see, this j should be equal to m, so I will replace bm in this j with m, and now this k should be equal to n, so I will replace this k with n. So we have am j will be replaced with m, and c k, so k will be replaced with n and en. So we have am bm times, sorry, this is amcm times bn en minus, this is ambm times cn en, right? So this ambm is nothing but a vector dot c vector, right? Because if you dot product two vectors, you will get, because these two are free indices, I mean sorry, these two are repeating indices. So m is repeating indices, there are no two indices here. M is repeating indices. So m will go from 1 to 3, so you'll get a1 c1 plus a2 c2 plus a3 c3. So that is nothing but dot product between a and c. Okay, so, and this is b and en, so this is nothing but vector b minus a and bm is dot product between a and b, and this is vector c. I think that's what we had to prove. A dot c times b minus a dot b times c. Yeah, so we have reached here. Okay, so you can ask me if you have any questions in this. So let me just tell you what we have done. So we had cross product between three vectors. We had to prove that this should be equal to dot product between first and last vector times second vector minus dot product between first two vectors times the last vector. So we have taken the help of convolution symbol. So b cross c can be written as epsilon ijk, bj ck ei, and a can be written as am en. Right, so there is a cross product, so I have taken all the magnitude terms to the left hand side. So epsilon ijk, am, bj, ck is kept here and are kept here, and em, which is a unit vector, has been cross product with ei. So em cross product ei will be epsilon nmi, em magnitude of ei, and then en, right? So and I was saying that this whole vector will be perpendicular to perpendicular to the plane which will contain these two vectors. Okay, because it is a cross product. Anyway, so em cross product ei can be written as e epsilon nmi em ei and en vector. So now there is a product between two permutation symbols. So free indices should be kept at last. So repeating indices should be kept at last. So here I is the repeating indices. So that's why instead of writing epsilon ijk, I have written epsilon jki, and I have, so this was ijk, I have just written jki, and this is still in cyclic order, so it's not going to affect its value. So now the repeating indices is at last, so we can just apply this definition here, and I've expanded and just applied the property of chronometer delta, and at last you will get this. Okay, so let me go to the next question. So we have question number 8. So this is a conceptual question, not any proof or any derivation. So question says, traction on So you would have studied traction in the lectures. So traction on how many planes are needed to completely define the stress at a point. So options are you need the one plane, or you need two plane, or you need three plane, or you need, I mean, none of this, more than three planes only, or you don't need any plane. So can you answer this question? So how many planes? So traction on how many planes are needed to completely define the stress? Okay, so you require three planes actually. You require traction on three planes to completely define a stress, because in the lectures you would have studied the definition of stress. So stress, which is a function of a point in a space, point x in a space, can be represented as sigma I going from 1 to 3, and traction vector I dyadic ei. So, you are able to see that this traction vector I is a traction on EIth plane, is a traction on a plane having the normal vector EI. So let's say you have three planes having normal vector E1, E2, E3, and traction vector on them is T1 vector, T2 vector, T3 vector. So by adding the dyadic product between the traction vector and the corresponding normals of the planes, you can get the stress. So in order to clarify this concept more, there is one more question. It says, um, suppose the traction vector on three perpendicular planes with normals A vector, B vector, C vector are as follows. Okay, so you have traction vectors on three perpendicular planes, and the plane normal are A vector, B vector, C vector. So these three perpendicular planes are not aligning with the Cartesian coordinate. So if these three planes would have aligned with Cartesian coordinates, then their plane normals would have been minus E1, minus E2, minus E3, which is not the case here. So there is some different set of plane normals here. Okay, so or it could be even E2, E3 also, but there is a different set of plane normal here. So now, so this traction vector on plane A is defined as, I mean, this traction vector with a plane having normal vector A. So on that plane, this traction vector is minus 1 times E1 plus root 3 times E2. So this traction vector B is root 3 times E1 plus 1 times E2, and this traction vector C is 10 times E3. You see that these three perpendicular planes have plane normals A, B, and C, and their traction vector on these three planes are TA vector, TB vector, TC vector, but these traction vectors are expressed in terms of Cartesian coordinates, not in terms of vector A and B and C. So A, B and C is not the basis vector actually as of now, because we have expressed the traction vector in terms of Cartesian coordinates. So E1, E2, E3 are the basis vectors. So, but we can express our traction vector in by making A, B and C also as basis vectors. So these A, B and C vectors are given as here. A is 1 by 2 root 3 times E1 plus E2, and B is 1 by 2 minus E1 plus root 3 E2, and C is simply E3. Okay, and it is also given here, and E1 vector, E2 vector, and E3 vector are the standard basis, standard basis in the Cartesian coordinate system. Okay. So even E2, E3 are standard basis, and ABC can be made basis actually, but that will not be a standard basis. So let's see. A is a normal. AB and C are perpendicular to each other, and magnitude of A is 1. You can just check 3 by 2 plus 1. So just recheck it. 3 by 4. Yes, so magnitude of A is 1, and magnitude of B vector. So that is also 1. Yeah, so that is also 1. So, and magnitude of C vector is also 1. So these are actually orthonormal, because ortho means ABC are perpendicular, and normal means they are normalized, their magnitude is 1. So A, B and C can also be made orthonormal basis. Anyway, so the next question, the question is, you have to write down the corresponding stress tensor. The corresponding stress tensor. So if we write down the corresponding stress tensor, so that can be written as sigma. So this should be equal to I going from 1 to 3. Fraction vector dyadic EI. So EI is normal to the plane. Okay, and these are the traction vectors on that plane. And this could also be written as, so this is in actually this definition here, sigma is expressed in E1, E2, E3 coordinate system. Okay, you have 3 traction vectors, so you can find out, you have 3 traction vector at a point, so you can find out the stress corresponding to these 3 traction vectors. Now it depends in which Cartesian, in which coordinate system you want to find out the stress. Let's say you want to find out the stress in E1, E2, E3 standard basis, standard coordinate system. So the traction vector will be expressed in standard coordinate system, and now the planes will be the planes normal to the coordinate axis. Okay, and you could also express your stress tensor in A, B, C. This is some different coordinate. I mean, this is some different coordinate system. So let's say you have this. Let's say you have this E1, E2, E3 coordinate system. And that should be clockwise actually. Yeah. And you have some different coordinate system. Let's say A, B, and C. So here there is A, B, and C. A, B, and C are normal perpendicular to each other, and they have unit, and their magnitude is 1. So, but it is not aligned with E1, E2, E3. So here you can express stress tensor in terms of stress tensor in this coordinate system or in this coordinate system also. So if you have expressed stress tensor in this coordinate system, so your traction vector should also be expressed in this coordinate system. So now you have traction vector expressed in coordinate system A times A plus traction vector on a plane having plane normal B. Now your plane will change because your one plane will be normal to A, another plane will be normal to B, another plane will be normal to C. So like that. So traction vector on a plane with normal vector C time dyadic this vector C. Right? So there are two representation of stress. Stress, I mean stress as a tensor will be same, but its representation will change. That's why its component will be different. In if you are taking even E2 E3 coordinate system or ABC coordinate system. So you can understand this with a vector. So let's say you have E1 E2 E3 coordinate system and ABC coordinate system. So vector will be aligned in that direction only in the space. So vector will be same, but its component will change depending on which coordinate system you are taking. If you are taking E1 E2 E3, so its component along E1 E2 E3 will have certain value. If you are taking ABC, so its components along ABC will have some different value. But vector will be same. Similarly, the tensor will be same, but its component will have different value in different coordinate systems. Anyway, so next question is related to that only. So next question says part B. So it says that write down the stress matrix in the coordinate system of both A, B, and C and E1, E2, and E3. Right. So I have told you it's very easy. So first let's write sigma in E1, E2, E3 coordinate system. So that will be nothing but I going from 1 to 3 T I divided EN, right? So if you write, so let's write that. So it will be T1 diadic E1 plus T2 diadic E2 plus T3 diadic E3. And T1 is TA actually because it's the first traction vector. So TA is already expressed in this Cartesian coordinate system E1 E2, so you don't have to do anything, just put the traction vector here. So already been expressed in E1 E2 E3. So I'm just writing here. So T1 diadic E1, so that will be nothing but T1 vector T1 vector just yeah, so transpose E1 transpose. So this is a definition of the direct product between two vectors, so that can be written as AB transpose. That's what I've written. So plus this vector T2 and E2 transpose, right? Plus this vector T3 times E3 transpose. So if you do that, so E1 is nothing but 1, 0, 0. So um, if you multiply these two, so E1 is 1, 0, 0. So you will get, so this is nothing but first component of first action vector, second component of first action vector, third component of first action vector times E1. So this is E1 transpose. So this will be a row matrix. So um, so this will be 1, 0, 0, right? Because it is E1 plus. Or I could do in matrix notation as well. I'm just expanding, but I'll try to do this in different notation also. Anyway, so let me just do it. So this is second vector, first component, second traction vector, second component, third component of second traction vector, and this is nothing but 0, 1, 0 plus this is third traction vector, first component, third traction vector, second component, and this will be 0, 0, 1, right? So if you evaluate, so it will be T1. So first will be T11, T21, T31. If you just multiply these two, other rows will be 0, other terms will be 0, plus this will be 0, and you will have T12, T22, T32, and other rows will be 0 and plus. Here you have 0, 0, 0, 0, 0, 0, and you have here T13, T23, and T23. So if you add all of them, so add all of them, so you get T11, T12, T13, T21, T22, T23, and then T31, T32, and T33. Okay, so this is what you're getting. So now if you see carefully, so this could be derived very easily from here also, because if you write here T1 traction vector 1 as T1I comma EI direct E1, so EI direct E1, so that will be, so this represents column, this represents row, so only first column will have non-zero values because it is E1, so that's what you are getting here, and this will represent to all the rows. Similarly here second column will have non-zero values, third column will have non-zero values. Anyway, so if you now see carefully, so this is nothing but here what you, this is first component, so this is traction vector 1 projected along E1, traction vector 2 projected along E1, traction vector 3 projected along E1. This can, I mean, this can also be represented as, so this was traction vector 1, right? And this is traction vector 2, and this is traction vector 3, isn't it? And this is expressed in E1, E2, E3 coordinate system, right? Because this is a vector actually, so this is traction vector 1, component of traction vector 1, component of traction vector 2, component of traction vector 3. Now one more important significance of this matrix is, you would have studied in the class, but I'm just recapitulating it for you. So this is component of traction vector 1 along E1, so it is T1 dot E1, and this is component of traction vector 2 along E2, so E1, so this is T2 dot E1, and this is T3 dot E1, right? So if you want to get first component of stress matrix, so sigma 11, this is sigma 11, so it is a component of traction vector 1 along E1. So E1 is a plane. So E1 was the first plane normal. So if you dot the traction vector with the first plane normal, you will get the sigma 11. And if you dot product the traction vector on plane 2, okay, with direction 1. So plane is 2 but direction is 1, so that will be a shear component, that will give you sigma 1 2. Again, if you dot product the traction on plane 3 in direction 1, okay, so you will get sigma 1 3. So similarly, this is traction vector 1 dotted with E2, traction vector 2 dotted with E2, traction vector 3 dotted with E2, and traction vector 1 dotted with E3, traction vector 1 dotted with, sorry, traction vector 2 dotted with E3, and traction vector 3 dotted with E3, right? Okay, so essentially what does it mean if you compare this with this value? So let's say you compare this with sigma 1 1 1 2 1 3, sigma 2 1 2 2 2 3, sigma 3 1 3 2 3 3. If you compare this, so the first one is traction vector 1, I mean traction on plane 1 in direction E1, so that will give you sigma 1 1, and second one is traction on plane 2, component of traction on plane 2 along direction E1, that will give you sigma 1 2. So here second is, so in the stress matrix, second indices is implying the plane and first indices is implying the direction. So this is the stress on plane 2 in direction 1, and this is stress on plane 3 in direction 1. So similarly you can just find out all the other meaning of all the other components as well. Okay, so now we have to find, so it's very easy, you just put all the components of T vector, TA, TB, TC. So TA was, so this will be, so here the components of TA will come. So components of TA was -1 and √3, and this was 0. And component of TB is second traction vector, so √3 1 and 0. Component of third traction vector, so 0 0. Pardon, this is 10 actually, not 1. So let me just correct it. This is 10 E3. No, not this. Yeah. So this is 10 E3. So here you will have 10. So this is stress vector expressed in E1, E2, E3 coordinate system. Now you want stress vector in. Now you want stress tensor and stress tensor. This is stress tensor in E1, E2, E3 coordinate system. Now you want stress tensor in, let's say, ABC coordinate system. So it's easy. You just express traction in ABC coordinate system, and your plane normals are also now ABC. So now you will have traction vector. So here what was, you can just compare with this. So sigma 1 1 is traction vector A in direction, you can say A, right? And this is traction vector B in direction A, and this is traction vector C in direction A. Similarly, this is traction vector A in direction B, traction vector B in direction B, and traction vector C in direction B. And this is traction vector A in direction C, traction vector B in direction C, and traction vector C in direction C. Okay. So if you are able to visualize, so this is a traction vector on plane normal A in direction A. This is traction vector on plane normal, on a plane with plane normal B, but it's in direction A. So it will represent the shear component on plane. This is a shear component on plane B, but in direction A. Similarly, this is a shear component on plane C, but in direction A. So now you just dot product all TA TA with A, TB with A, and TC with A. So if you will do all these dot products, so let me just do this for you. So TA with A will be, just see what is T and what is A. So you will get minus root 3 by 2 plus root 3 by 2, so that will be 0. And TA with B, so that will be 1 by 2 plus 3 by 2, so that will be 2. And TA with C, so that will be 0 again. You just have to do dot product between these two vectors. So TA with A, so if you do that, so you get minus 1 by 3 and plus 1, I mean minus root 3 and plus root 3, that will be 0. TA with B, so here you will get minus root 3 and plus root 3, that will, okay, sorry, TA with B, okay, so you'll get 1 plus 3, so that will be 4 by 2 times 4 by 2, so that will be 2. That's what I will do. And TA with C, so TA with C, so C, there's no E3 here, there's no E3 here, and this is E3, so this will be 0. That's what I will do here. Similarly, you can find all the other components, and so if you find all the other components, your stress tensor in coordinate system A, B, and C, so it will be 0, 2, 0, 2, 0, 0, and 0, 0, 10. You substitute all these values here, all these values here. So this is in different coordinates. So you see here that in the coordinate system ABC it has these components, and in the coordinate system even into E3 it has these components. So the components are different actually in different coordinate system, but the stress tensor will be same. One more way to derive this is actually, so let's say you want to derive, you can just try this on your own. So if you want to derive in ABC coordinate, so I had written that it will be TA direct A plus TB direct B plus TC direct C. Now you will see that you will say that how to find T in in the coordinate system ABC. So let's say I just want to find the component of T along A. So let's say TA along A I want to find. So that will be, so actually T can be represented at, let me just, so traction vector T can be represented in, traction vector TA can be represented in coordinate system ABC as, that will be traction vector TA dotted with the basis vector A. So okay, so this is projection of traction vector TA along A, and so this is in direction of A, plus projection of traction vector A on B, and that will be direction B, and projection of traction vector A along C, and that will be C. So this is TA, and this you will get TB as projection of B along A, so that will be A, projection of B along B, so that will be B, and projection of B along C, so that will be along C. Similarly TC, so that will be traction vector C along, projected along A, so that will be along, direction will be along A, traction vector C projected along B, so that will be along B, and traction vector C projected along C, so that direction will be C. Now you put all these values in here in this formula, so you'll get TA direct A. So I'm just doing first one. So TA direct A will be projection of A along A, and then A direct A plus. So just put here, so projection vector A along B. So TA is coming to the left hand side, so that's why this vector will come on the left hand side. So this is B direct A plus projection of A along C, and that will come along. So this is along C and this is A, so C, it will be C radic A, and so on. You can calculate all the components. So this A radic A, so this, if you have a stress tensor in if you have stress tensor in coordinate system A, B, and C, so this A radic A represents, so now you have rows and columns represented by A, B, and C. So let's say here you have, I'm just writing A, B, C, and here also you have A, B, C. So let's say we have these components. So, so this A radic A, so it's the component at ath row and ath column. So this will be TA dot A here, and this B radic A, so this will be bth row and ath column. So this will be here. So this is TA dot B, and this third one will be C radic A. So this is cth row and ath column. So will come here. Similarly, you can fill all the others by, if you do all the direct products, you will get all the other components. So, but it is matching with this here. You see here TA dot A, TA dot B, TA dot C. Here it is matching. TA dot A, TA dot B, TA dot C. Others also will match. So you see here that I have expressed traction vector in the Cartesian in the coordinate system A, B, C, and now I have done direct product with the definition of stress tensor in the coordinate system A, B, and C. I have just done the direct product, and now it is giving you all the components of the stress tensor in coordinate system A, B, and C. This is a more generalized derivation. Okay, so I'll stop here. Actually, I'll stop here for now. If you have any questions related to this, you can ask me in the next live session, which will be, I mean, my live session will be, there are two live sessions. I'll take next live session on Tuesday at 7 p.m. Okay, so I'll stop here. So thank you. Thank you
Thank you, sir.
for attending. You can still ask doubts if you have any. There are one or two more questions I wanted to cover. So let's cover one more question. Maybe we have 5 minutes left. The question says you have, so I just write question number 10. So let's say you have okay. So let's say you have stress tensor whose components are 1, 2, 3, 2, 4, 6, and 3, 6, 1. Okay, and these are in even E2, E3 coordinate system. So you have to mention coordinate system also when you're mentioning stress tensor or some vector. You have to specify in which coordinate it is, because if you will just write the components, and how we will know in which coordinate system these components are. So this stress tensor is E1, E2, E3 in the coordinate system E1, E2, E3. Now you have to find traction vector. So find traction vector at point P on the plane whose normal are whose normal is in direction E1 minus E2 is 2 E3. So you know that firstly you just find the plane, you just normalize this plane normal. So normalized plane normal will be E1 minus E2 plus 2E3 divided by its magnitude. So its magnitude will be 1 square plus 1 square plus 2 square. That will be 6. So that will be under root 6. So this will be 1 by root 6 times E1 minus E2 plus 2v3, right? Now you have, so definition of traction vector is traction vector can be written as sigma times n, right? So just do this. So sigma was 1 2 3 2 4 6 and 3 6 1. So if you do this, so components are 1 minus 1 and 2, and obviously 1 by root 6 is a scalar, so it will come here. If you solve this, so you'll get traction vector as 5 by root 6. Actually you'll get vector, so 5 by root 6. These components are, let's say, 5 by root 6, 10 by root 6 and minus 1 by root 6. So you will get a vector. So this is first component is in even direction, so we can just write 5 by root 6 times e1 plus 10 by root 6 times e2 minus 1 by root 6 times e3. Okay, so that's how you can solve. And why we have done this? Because we just have done the previous question in that this was the, okay, this component was the component of traction. This is sigma 1 1, so this is component of traction 1 in direction 1, and this is component of, so let me just see, yeah, so, and this is component of traction 1 along direction 2, and this is component of traction 1 along direction 3. Okay, so here actually this traction is acting on plane 1 only, and it has different directions. So this represents different directions, and each component, so this is corresponding to one plane and in different directions. So, and this is second plane, this is third plane, and direction are changing with columns. So if you will multiply your stress tensor with any direction, so it will give you the traction vector on that plane. And this is direction of the plane now. Okay. So we will stop here for today. Yeah, thank you. I will stop the recording now.